Hello and welcome to module 6 on source coding. Let's look at the outline for today's talk. We do a brief recap on Huffman coding, which we studied in the previous lecture. Then we will look at something called arithmetic coding, followed by Lempel Ziv coding, and then do something called run length coding. So these all are source coding algorithms, and we would definitely look at some examples. So that is the agenda for the day. We start with a brief recap. We did look at source coding theorem. It tells us what is the best we can do in terms of compression. We then defined the efficiency of a code, followed by some examples on Huffman coding. We also saw that coding in blocks helps. So let's quickly refresh what we did regarding the Huffman coding with an example. So Huffman coding requires you to first arrange all the probabilities in a decreasing order. So we write the symbols and write down the corresponding probabilities in decreasing order. What we do is we combine the bottom two one into a composite symbol with a probability Pn plus Pn minus 1, and then we combine the next bottom two and so forth to add up the probabilities, and this tree keeps elongating and the probabilities keep adding up till we reach 1. We did this following example where we had these 7 symbols and the probabilities were arranged in decreasing order, and we constructed this Huffman tree based on the probability. So if you see, the last two combined to give 0.03 and 0.04 and 0.03 add up to 0.07 and so forth, and we go up the tree and we quickly see that it adds up to 1. And now finding out the code words is pretty simple going backwards. So for example, for x4 we start right at the mother node and we follow the path back to the desired symbol, but each time we bifurcate, we add either a 1 or a 0. If we go down the ladder, we add up 1. If we go up the ladder, we add a 0, or we could interchange these. So for example, if x4 was to be encoded, I go down, so 1, 1, 1 and up means 0. So I will get x4 to be 1, 1, 1, 0, and this is called the Huffman tree. You can always plug in the values of probabilities to determine h of x and r bar, which is the average code word length for this. If you look at the formula, h of x is nothing but, with a negative sign, summation pxi log to the base 2 pxi over all i's, or in this case k, and you get the values of h of x, and similarly r bar is the average code word length, and you can get the value of the average code word length. So efficiency is the ratio is less than 1 in this case. So this example is illustrative in the sense that the self information as shown in this table, they are not integers, and we will see this is the biggest problem with prefix codes like Huffman, which are unable to exactly map it. We also saw in the last class that if we work block by block, then we have a better chance to do so, and this is the reason why. Suppose we encode a block of b symbols at a time, right? Then we write the equivalent source coding theorem as b of hx less than or equal to rb, which is the average length for one block of b symbols, and so forth, less than b hx plus 1, coming back from the source coding theorem. And we saw in the last class that if you divide both sides by b, you see that your h of x is the lower bound, but now the symbol per symbol, if you find out the number of bits per symbol, which is rb bar divided by b, is limited, upper bounded by h of x plus 1 over b. So this is important. As we increase the block size b, I can pinch it harder from the top and squeeze it to become closer and closer to h of x, right? That is the whole thing. If we look at a practical example of this, suppose we have our friend tossing a coin. So, we have a source A and this guy is tossing a coin, but this coin is a fair coin, and every 1 second it tosses a coin. If a head comes, it says 1, if a tail comes, it says 0, 0, 0, 1, 1, it churns out this bit stream. Okay. On the other hand, I have another source B, which is another person with a habit of chewing a gum. So, he has stuck some chewing gum on one side of the coin, and this time it is a biased coin. But his definition, work definition is the same. He tosses the coin once every second and spits out 1, 0, 0, 1 randomly. Okay. Now, if you see source A, the h of x is 1 bit, whereas in this case h of x is less than 1. Consequently, we should say that we should be able to use fewer number of bits on an average to send the output of source B as opposed to source A. But here I am at a dilemma, because source B is also saying 1 bit every second, because the person is tossing a coin, and if a head or a tail comes, it speaks out 0 or a 1. So, the way to go about it is, we can always look at, say, blocks of B. And we already know that probability of head, for example, is 0.2 and probability of tail is 0.2 or 0.8 for example. So, they add up to 1. Then it is easy to form a table right from 0, 0, 0, 0, 0, 1 right up to 1, 1, 1, and we have this associated probabilities, right. So, this will be 0.2 raised to the power 3 and this will be 0.8 raised to the power 3 and somewhere in the middle, and they add up to 1. So, you will see that we have now, these are my new symbols, and this source B does not have to say a 1 or a 0 or a 0 or a 1 depending upon the outcome of the head or a tail. It will wait till 3 tosses and look at this combined symbol, and it has a probability. So, these can be written as your A, B, C, D, so and so forth, and they have their own Huffman code. So, a variable length code will be actually used to send out these composite symbols, and if you see on an average, you will be able to have the average bits per symbol, so to say, will be less than 1 bit in this case. So, you actually require fewer than 1 bit to represent the outcome of this biased coin toss. But this logic will not be true for fair coin, where if you combine them in blocks of 3, 4, B, it does not matter, they are all equiprobable and you will not be able to get any compression because of the combination into symbols. So, this is a simple example that illustrates why if you do block by block coding, you should be able to do things better. We also did a simple example where we had 3 x1, x2, x3 with the associated probabilities and the self information and the code words, and we calculated h of x to be 1.5589 bits and r bar, the average bits per symbol, 1.6 bits, and the efficiency was 0.97. Now, we did a simple experiment, we made pairs. So, my B block length is 2. So, I have x1, 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 x2 and so forth up to x3, x3, and I can multiply the probabilities to get the net probabilities here, recalculate the self information, and we do an Huffman coding to get this following table. Again, if we calculate the average bits per symbol, it comes out to be 1.588 and h of x is 1.5589 bits. Now, how does it compare with the previous one? Well, previous one the efficiency was 0.97 and this time we have improved upon our efficiency. So, we are going closer and closer to your 1.55 in this case. We have been able to get to 1.58, but maybe 3, 4, 10 blocks at a time we can reach better and better. Of course, it comes at a cost. The cost is the computational complexity that is involved in both encoding and decoding. So, that brings us to the problem of these prefix codes, right. The prefix code try to match the self information of the symbols with the length of the code words, but the lengths as we observed are integer. So, sometimes we are better, sometimes we are worse off. The exact match is possible if and only if the self information is an integral number of bits. So, let us look at this more emphatically. So, we are trying to see when does that happen, when does the exact number of bits in self information is an integer. So, we look at this table quickly. Again, we have this very special 7 symbols with very unique probabilities such that the self information is integers, and the code word length is easy to match and they match exactly, but this is possible only because of a very unique probability distribution. Fine. So, we now again look at why prefix code work, but they can work better. What are the problems with prefix codes? Where do they fail? So, prefix code as we saw are based on trees. So, Huffman tree helps you to make the Huffman code. So, let us look at another example where we have the symbols A, B, C, D, E and F, and suppose they are decreasing order of probability. So, P1, P2, so on and so forth, right, P3, P4, P5, P6, and you combine the bottom two to achieve this Huffman tree. Okay. It is fairly mechanical, but whenever we go back and whenever we hit any of the bifurcations, we have to take a decision whether to go up or to go down, right, and we always attach one bit either which way, whether we go up or go down. But what is telling us, right, because these two branches are the sum of the probabilities. So, suppose here the probabilities are 0.1 and 0.1, then going up and going down requires a decision of one bit. On the other hand, if it was 0.1 and 0.2, then things are not the same, because information theoretically, right, we should not ascribe the decision to go down or up does not warrant equal number of bits, because they are not probabilistically equal. Okay. So, if you look at the slide, if we have a case of 0.5 to 0.5 as opposed to 0.9 to 0.1, we should not give equal number of bits in both the cases. Why? In the latter case of 0.9 and 0.1, because suppose these two branches finally add up to 1, right, it would only take 0.15 bits to select the first branch and 3.32 bits to select the second branch, because 0.1 is rarer than 0.9 probability, and therefore, I need more number of bits to represent that. but the Huffman code will always ascribe 1 bit per decision. So the d-adic probability distribution which we saw is the unique case where we have this decision at all stages you will have 1. So if you look at this d-adic case, we have x1, x2, x3, x5, x6 and x7, and if you look at the probabilities, it is 1 by 2 raised to power 6, 1 by 2 raised to power 5, 1 by 2 raised to power 4 cubed, 2 square and half. Very special distribution. Special in the sense both sides are equiprobable and they add up to 1 raised to 2 raised to power 5. Again, when we go for combining, both sides are equiprobable. So you get 1 2 raised to power 4. Again, when we go for a combination, very unique, but they are equiprobable. So whenever we assign one bit going up or down, we are doing justice again. And so on and so forth. So you will see at all stages this is the only distribution that going up, going down will add up to 1. And this tells us that why this d-adic distribution and only this one will allow us to really reach the efficiency of 1. Okay. This is an example why we should be able to get the best possible compression in this case using Huffman code. Okay. So efficiency is clearly 1 in this d-adic probability distribution. So we need to get around this problem, and for that we propose this technique called arithmetic coding that does not have this restriction of this integer bits being assigned. We need to get on the real line because the probabilities can be as fine as possible. Okay. So we definitely should not restrict ourselves to assigning code words right in the beginning. Let us play along the real line where we can have as much resolution as possible, and only at the end should we talk about coding it into bits. Very simple logic. Let us see how we do it. Okay. So it works by representing the file to be encoded. What do you mean by file to be encoded? Let us say we have symbols, your English language text, you can have images, you can have any other representation, a string of symbols, but in this case let us just talk about a series of English alphabet. So we have to compress this file which has several English alphabet. So what we do is we keep subdividing the line between 0 and 1 subsequently, successively as the symbols come in, and we go deeper and deeper into the line. So let us look at a simple example. Suppose we have only 3 symbols consisting of A, B and C. So whatever be a bit stream, it is only a some combination of A, C, C, B, A, B, C or any other random combination. This is just a toy example for illustration. Now suppose we have the probabilities associated with it. Only when the probabilities are different do we have a scope for compression. So in this example, let us say PA is 0.5, PB is 0.25 and PC is 0.25 again. So how do we begin? We have our real line from 0 to 1, we divide it into 3 intervals proportional to their probabilities. So look, numbers are resources. This real line is a resources, it is a real estate. We would like to divide this real estate into this equal for P, B and PC which have 0.25 probabilities, whereas PA which has a higher probability will require 0.5, so half the line. So, let us graphically look at it. We have 0 and 1. This is our scratch pad, this is where we are going to work. Now, we have these three probabilities 0.5, 0.25 and 0.25. Okay. So, why don't we divide it? So, half the line is the domain for P. What does it mean? From 0 to 0.5 is my region for A. 0.5 to 0.75 is my region for B, and 0.75 to 1 is C. So, very mechanical, I am just distributing the resource. Now, let us continue with our example. Suppose the bit stream to be encoded is BACA. Okay. So, B comes first. So, we focus our attention on B. Since B has come, if you consider the previous example, B lies between 0.5 and 0.75. So, that is the thing we go, but then we scale up this 0.5 and 0.75, stretch it up, and we will use this as the real estate to divide further between A, B and C in the same ratios. So, B, which was the first symbol that came in, chose this subinterval 0.5 to 0.75. Now, this subinterval will be further subdivided into three regions A, B and C, half, quarter and quarter, depending upon the probabilities of A, B and C. So, now 0.5 to 0.75, if you divide it half, then it will become 0.5 to 0.625 belonging to A, 0.625 to 0.6875 to B and 0.6875 to 1 for C. So, let us look at it graphically again. We started with this real line 0 to 1, A had the line's share of 0.5, B quarter of it and C again quarter of the line. First symbol to come was B, right. It is not very visible, but this B has come in first, and so I take this section for B which belongs from 0.5 to 0.75 and stretch it. So, the upper limit is 0.75 and the lower limit is 0.5, and again I quickly divide it into three portions equal to or proportional to the probabilities. So, A gets again half of it, but what is half of it? 0.5 and 0.75, add it up and divide by 2, 0.625. So, that is the line for A, and then subsequently divides 0.625 and 0.75. So, add them up and by 2 you get 0.6875 and so on and so forth. Now, please make an observation that as we proceed, the boundaries are represented by numbers, decimal points, but these are becoming larger and larger. So, earlier it was 0, 0.5, 0.75 and 1, now it is 0.5, 0.625, 3 digits, 0.6875, 4 digits, 0.75, 2 digits. So, I am now requiring more and more numbers to represent my boundaries. Anyway, so I was working with B, and then next number that comes in, the next symbol that comes in is A. So, the A comes in, my boundaries become from 0.5 to 0.625. So, I stretch it up. So, 0.5 remains 0.5 and this one becomes the upper limit. So, now I am at, this is my real estate to divide, and rest is mechanical, half of it. So, midway point nothing but 0.5 plus 0.625, add them up and divide by 2. So, you get 0.5625 and then same with 0.59375. No surprise, I am using more number of larger points after the decimal to represent the boundaries. Next comes C. So, I have already encoded B, A and now go to C, and it is the same mechanical, I stretch it out to 0.625 as the top and 0.59375 as the bottom, and when A comes in, again I get the middle point, and you get the feeling, right. So this is the way to go about doing this arithmetic coding. And suppose I say I have had enough, why don't you now tell me what is the code word for BACA, right? What is the code word? Well, I am not giving you one symbol at a time, I am giving you the entire code word for BACA, and the answer is 0.59375. Any number between these two boundaries, 0.59375 and 0.609375, any number, pick at random, is a valid code word for BACA. Okay? Pardon?
So there will be infinite numbers can be.
Okay, the question being asked is there can be infinite choices. The answer is no problem. At the end I should be able to uniquely decode it. And how do we decode it? Well, it is the same thing. Suppose I say, look, I have received 0.59375 at the receiver, tell me what was sent. So I said, okay, no problem, let us locate it. Where is 0.59375? So I go to my real line between 0 and 1 and see where is it located, where should this number 0.59375 lie. So I said, oh, this number should lie in this region somewhere. I don't care where, just this region. So say, oh, this is the region for B. So first decoded symbol is B. But am I done with? No. So I go further. So I divide this B section here and I still ask my question, tell me where is 0.59375 would lie. And then I said, oh, 0.593, it is bigger than 0.5, but it is less than 0.625, it should lie in this region. I don't care where exactly it lies, it is in this region. Fair enough? So my second decoded symbol is A, but I am not done yet. So I expand it further, mechanical. And I said, where does 0.59375 lie? Now I go ahead and say, okay, this is in this region C, right? It could have been anything above it also, but it is this region. And then I say third symbol is C, and I expand it further and I see where does it this lie, and then I get the answer as A. And you will be surprised to see that any one of the numbers in this region would give you the same answer. But if somebody doesn't tell me when to stop, I will keep going. And after BACA, I can give you a few more CCABBD, or D is not there, but ABBA. So I need a way to tell me when to stop. So a stopping flag or a cue is required for arithmetic coding. But in this example, we just found out that how arithmetic coding can be effectively done. So my 0.59375 could be now represented as bits and sent. So this
at the time of encoding, we have to know all the symbols at a time. Means all the symbols. Otherwise, we don't enable to code the by using arithmetic coding.
Okay. So the question being asked is, are we required to know the entire symbol stream to do that? Well, the answer is yes, because unless we keep going symbol by symbol and encoding, we will not be able to reach the final 0.59375 as an answer. So yes, we decide to go by blocks, and that helps us in the decoding process. So it is a, so to say, protocol, for example, to say that I will only encode 50 symbols at a time. So I take 50 symbols and don't send anything, I don't declare my code word till I encode the 50 symbols. And then I have some answer 0.5937221922275, whatever. And then that can be represented as bits and transmitted.
So the number of bits required to represent such a fine number can be more than the actual number needed to encode ABCD side.
Okay. So let me rephrase the question. The question being asked is it possible that the actual number of bits required to represent this fine decimal number be actually more than what we would have done otherwise, say by doing Huffman coding, because after all I have these probabilities, so nothing stops me from using a Huffman code. The answer is no. Arithmetic coding offers a much better compression than your standard Huffman coding, and the reason is because it keeps working on this real line and it starts matching the occurrences of A, B and C to as fine as possible. This goes very fine. Nowhere at any stage we are putting a restriction on the self information being matched to the actual number of bits, because nobody is talking about bits. Bits will come at the end. So it will come out to be a winner as compared to Huffman coding. You can try this out, but the reason why it works is it is not plagued by the problem of trying to match the integral number of bits in the code word to the average self information. That is the reason why this works much better. Okay? But it is worthwhile trying out a simple example to compare the efficiency of arithmetic coding to Huffman coding. So both arithmetic coding and Huffman coding form a part of the JPEG compression standards, but both of them have this requirement, and the requirement is that you need the probabilities of A, B and C a priori. Without that I can't even take the first step. Now it also does not have any, so to say, bias towards whether B, A, C are dependent on each other. We are treating them as independent. Same with Huffman, same with arithmetic. But if it is in English language, I, N, G come in a pair, T, H, E are more frequent. So Q followed by U is more common. It does not take care of that. And the problem is that in reality, who can tell me what is the probabilities of A, B and C? Can we work around this problem? And the answer was proposed by Lempel and Ziv in their algorithm. So the shortcoming of Huffman is that it requires symbol probabilities, so does arithmetic coding. But in most real life scenarios, symbol probabilities may not be known in advance, or even if you know, they may be changing over time. Okay? The symbol may not be time invariant. The probabilities might just change. And Huffman coding is great for discrete memoryless source. Okay? So occurrence of one symbol does not affect the occurrence of the subsequent symbol. An occurrence of a Q will not influence whether a U will appear after that, but that is asking for too much. So clearly Huffman coding is not the choice, not the best choice really for a source with memory, where we have those sources in real life. And we looked at this example, Q followed by U or TH or ING do occur more frequently. So we are talking about compression of an arbitrary sequence of bits, and it is possible by coding a series of zeros and 1 as some previous such string plus one new bit. So the basic philosophy of Lempel Ziv algorithm is as follows. It tries to represent any future string as something that has already arrived. So it encodes future strings in terms of past strings. So the new string formed by adding a new bit to the previously used prefix string becomes a potential prefix string for future strings. So, thus these variable length blocks are called phrases, and phrases are listed in a dictionary which stores the existing phrases and their location. So, all we have to say is location number so and so plus an innovation bit which makes it different. In encoding a new phrase, we specify the location of the existing phrase in the dictionary and append the new letter. We will look at an example. Suppose we wish to encode this long string 1010111011 and so on and so forth. Okay. This is our target bit stream to be encoded. We begin by doing something called parsing, which is a comma separated phrase that represents strings that can be represented by a previous string. So, let us again revisit this string 10101 and so forth, and I put a comma after the first one, right, because we are starting from scratch, right. So, it has a null prefix and a 1, and then we get a 0. So, we express the second comma as after this 0. So, what it means is this 1, it is right in the beginning, we can't really express it in terms of any other previous bit, it is actually starting off with a 1 and a 0. In some realizations of Lempel Ziv, we already assume 1 0 being the first two entries of your code book, but here we are starting from scratch. Now the real fun will begin. Okay. So far a dictionary contains a 1 and a 0. It is not a surprise because we are binary encoding and everything will be represented in terms of 1s and a 0. But now let us look at the further parsing of this string. So, we already have 1 comma 0 comma and then we encounter a 1, but we know that 1 is already in my dictionary and that too location number 1, but 1 0 is not in my dictionary. So, this 0 makes this symbol, this is my new symbol 1 0, different from what is present. So, this 0 which made it different is called the innovation bit. So, now I put a comma and then I proceed further. The next bit I encountered is a 1, I look into my dictionary. So, this is my small dictionary, a horizontal dictionary which has 3 entries 1 0 and 1 0. I have encountered a next 1. Is it present? Of course it is. So, I proceed and I look at this 1 1. Is it present? I scan my dictionary and say no, 1 1 is not present. So, I put a comma behind 1 1. Okay. Having put a comma, I now proceed further. I encounter a 0. So, 0 is present? Of course it is present, that too in location 2. I encountered a 1. So, 0 1. Is it present? No, it is not. So, I put a comma because 0 1 is another parsed symbol. And then I proceed further from this point onwards. I encountered a 1. Is 1 present? Sure, it is present at location number 1. Is 1 0 present? Oh yes, it is present, location number 3. So, I proceed further 1 0 1. Is 1 0 1 present? No, it is not. So, I put a comma after 1 0 1. Okay. And I proceed further along the same lines. So, I get 0 1 0 comma and then 1 0 1 1 comma and so forth. Now, if we make this observation, as we go on parsing, these code words become longer and longer. At this point it is not fair to call them code words, but these parsed bits become longer and longer. So, 1 bit long, 2 bits long, 3 bit long, 4 bit long and so forth. So, we end up representing future bit streams in terms of the past bit streams. Now, if we complete this example, we can say that time has come to represent these parsed bit stream as fixed length code words. So look at the first one. It's null because it really cannot be represented anything that comes before it. So it's 0 0 0 and innovation bit is 1, so 1. So why don't we bring it closer? Okay, so that's better. So now this 1 is represented as 0 0 0 1. The next one will be represented by a code word. Again 0 cannot be represented by anything before it, so this is a null 0 0 0 and the innovation bit is 0, which makes it different, so 0. Then we look at 1 0. Okay. So 1 0 of course has a 1 and an innovation bit 0. 1 can be represented by a previous code word, but where is it present? Location 1. 1 is presented at location 1. So the first 3 bits are only indicating the location, where, which code word. It says 0 0 1, location number 1. And what makes it different? Addition of a 0. So 0 0 1 0. Let us look at this 1 1. So the first one is previously present, location number 1 represented by location 0 0 1 and the innovation bit 1 just adds right here. Let us look at 0 1. 0 1 is 0 followed by a 1. 0, where is it located? Location 2. Location 2 is represented by number 2. 0 1 0 is number 2 and 1 makes it different. What about 1 0 1? 1 0 1 is represented with, this is at location 3 1 0. So location 3 0 1 1 and innovation bit is 1. Okay, and subsequently you can look at all of them. Please note that 1 bit is also represented as 4 bits, so expansion. 1 bit is represented as 4 bits, expansion. 2 bits as 4 bits, 2 bits at 4 bits, 3 bit as 4 bits, 3 bit as 4 bits, 4 bit as 4 bits. So far we are losing in terms of being efficient in terms of coding, but please note as we go along parsing, longer and longer strings will be there, but all of them still will be represented by 4 bits. So we will start getting our compression advantage as we go along. Okay. So the first few symbols will not actually yield compression, they will end up expanding the number of bits. See, the number of bits on top is larger than the number of bits which are originally present, but the case will drastically change as we go along. So what have we sent out as an encoded bit stream? Code word at location 0 followed by 1, so 0 0 0 1, code word at location 0 followed by 0 0 0 0 and so on and so forth. So if you just write it out without the commas, I send out this 0 0 0 1, 0 0 0 0 and so this is my encoded bit stream. So binary string encoded into another binary string. Now what do I do at a decoder? Well, decoder knows, since he is a friend, that we are doing a fixed length code. So fixed length code means every 4 bits represents a symbol. So I look at the first 4 bits, it's 0 0 0 1. Within this I also know that the first 3 bits represent the location and the next one is my innovation bit. What makes it different? So location, null location means it is the starting one. So I have the first entry 1 in my decoded. Does everybody see that? So the first entry which I decode is the bit 1. First 4 bits are gone. I concentrate on my next 4 bits, which is 0 0 0 0. And then the first 3 bits represent the location, null location, and the fourth is an innovation bit 0. So clearly I write down immediately 0. So the first 2 bits are 1 and 0, and the first 8 bits are decoded. So 9, 10th, 11th and 12 bits, if we look at it, and now you can actually see, because these two are the same, the upper bit stream, lower bit stream, but they are represented by commas. So the decoder is actually looking at, mentally it is compartmentalizing it into 4 bits at a time. So we are now looking at the third bit, third symbol, it's 0 0 1 0. So what does the decoder do? It knows that the first 3 bits are the location. Aha, the first location we have found out is 0 0 1, but we already have decoded the first entry, and what was that? It was 1. So it is 1 and the innovation bit is 0. So it completely knows what was sent, it is 1 0, and it again looks at the next 4 bits and knows it is 1 1. But then it looks at this fifth one, it says 0 1 0 second location. What is in the second location? Bit 0, and what is the innovation bit? 1. So 0 1, and so on and so forth. So decoding is pretty easy, it can be done very simply in a Lempel Ziv encoding algorithm.
Yeah.
Yes.
If the code was longer, then you would be needing more bits to represent the location. You won't be able to specify the location in 3 bits. Then you would be needing say 5-bit strings for each number. Then it won't be efficient.
Okay. So let me tell the question, repeat the question. The question being asked is, the number of bits used to represent the location depends on the length of the table, the size of the table, right? And as we form a longer and longer encoding, our size will increase, because there will be more and more code words, and eventually there will be an overflow. The observation is correct, and so we need to have a sufficiently long indicator for the location. But the second observation is not correct, that whether it will be less efficient. In fact, it will still be a lot more efficient, as we will see in the subsequent slides. So if we are to complete this example, we have this dictionary location. Now we made this horizontal dictionary into a vertical one. So we have a dictionary location, and we have a content, and we have a fixed length code. As observed, if the dictionary length increases, the fixed length code word will have to be longer, because the location for the dictionary, right, will require more number of bits. So 3 bits can only represent a dictionary of length 8, 4 bits can represent 16, 5 bits 32, 6 bits 64. So it is growing exponentially. Just adding 1 bit can double the size of the dictionary. So there itself, it tells us that there is a lot of hope in this method. Just adding 1 bit takes care. So once I am in 1024, adding 1 more bit increases the size of the dictionary by another 1000, and then another 2000, and then 4000. So I will be very happy when I am working with a long dictionary, okay? And in general we are working with larger dictionaries, but we have to fix this a priori. That is the catch. We cannot say that we will decide this fixed length code word at a later stage. If it has to be 12, you tell me what is the anticipated size of the dictionary and fix the code word length accordingly. So as you can see that this locations must correspond to the fixed order. Here we have 7, and therefore we need 3 bits to represent the fixed length code word. So let us just comment a little bit on the length of the table. What should the length of the table be? Because we just now saw that overflows are a reality. So in practical application, regardless of the length of the table, it will eventually overflow. This problem can be solved by pre-deciding a large enough size of the dictionary. Again, it is the best bet we can have. The encoder and decoder can update the dictionaries by periodically substituting the less used phrases from the dictionary by more frequently used ones. Now we come to another encoding technique called the run length encoding. It is an interesting source coding technique. It is a technique used to reduce the size of a repeating string of characters. So, it is not applicable everywhere, it is for only when we have runs of lengths, runs of zeros or 1. So, what is a run? Well, if you have a 0 0 0 0 0 0 many times over, it is a run of 0. Similarly, a run of 1. Okay. So, run length coding can compress any type of data regardless of its information content. But the content of the data, the number of runs we have actually will decide the efficiency of run length coding. And it is supported by most bitmap file formats like TIFF, JPG, BMP and so on and so forth, and very commonly used in fax machine. Because in fax machine, where we have the page mostly blank and characters written on top, if you represent a white pixel by a 0 and a black pixel by a 1, we have huge runs of zeros. So, it is very efficient for fax machine. Let us look at an example. Let us look at this strange bit stream. It has a long run of 1, then a run of 0, then a run of 1. We have taken this peculiar example because this effectively shows where run length encoding will work. So, what do? We count the number of ones and we said okay, 15 ones, count the number of zeros 1 2 3 4 up to 19, 19 zeros and then 4 ones. So, now this long bit stream is nothing but 15 comma 1, 19 comma 0, 4 comma 1. So, it says how many and the after comma of what, how many of what, how many of what. Okay. So, here since the maximum run is of 19, well, we can represent it with 5 bits. If we anticipate runs can be of the length 30, then also 5 bits would suffice. Or if the run lengths can be as large as 35, 40 up to 63, we will require 6 bits to represent. But clearly, this simple representation of this long bit stream shows the power of run length coding. In this case, the compression is 1:2.1 in this simple toy example. It is very high for fax machine applications. So, let us now summarize today's lecture. We revisited the Huffman coding and figured out why it works and where it fails. Then we looked at arithmetic coding, which is a little bit more efficient, and then we looked at Lempel Ziv coding, which does not require a priori the probabilities of the symbols, and it also works for sources with memory. And finally, we looked at an example of run length coding. That brings us to the end of module 6.